Good afternoon, everyone. And it's our great honor that we have Hidetoshi Nishimori visiting us today from Tokyo. Nishimori-san is a professor of physics at the Tokyo Institute of Technology, and he is actually an old hand in the theory of quantum annealing spin systems, and he has thought about many of the problems we are excited about today already 10 or 20 years ago. He's actually an author of 100 plus papers and 2 books on the topics. And he actually got his PhD also in Tokyo at the University of Tokyo, but spent his postdoc years, or some of his postdoc years here in the US at Carnegie-Mellon and Rutgers universities. And he won 2 prestigious prizes, the Nishina Memorial Prize and the IBM Science Prize. And we are very curious to hear about his latest work, and he will present a little bit more general topic talk on the theory of quantum annealing. Nishimori-san.
Thank you very much. I'm very happy to be here to talk in front of people in Google and others. So I was working on statistical physics. I was, but I'm now relatively heavily working on quantum annealing. So I will talk on this latter topic today. The title is, as written here, Theory of Quantum Annealing. So let me set up the framework first of the structure of my talk today. It's about quantum computation. And the very well-known, or the best-known framework of quantum computation is the gate model, in which you prepare a set of qubits, quantum bits, linear combinations of zeros and ones. And you apply quantum gates, unitary transformations, to those sets, one by one, discretely, and change the state of the system toward the goal. And quantum annealing, or quantum adiabatic computation, is another paradigm of quantum computation. And the goal, at least the current goal that is actively sought after, is to solve combinatorial optimization problems as efficiently as possible. So the problem itself is classical. No quantum mechanics appears in the problem of combinatorial optimization itself. But we use quantum annealing, quantum mechanics, to solve it. And it is now known that these 2 paradigms are equivalent with polynomial overhead. However, we set a specific goal for quantum annealing today to solve combinatorial optimization problems. So let me focus on this aspect. And another reason is that quantum annealing has been realized as hardware by D-Wave systems, as many of you may know. When I proposed the concept of quantum annealing, I never expected that someone will manufacture such a machine. It's a crazy idea. But they did it, and they sold it. So it's very amazing. Anyway, it's not about experiments. It's about theory today. So we want to solve combinatorial optimization problems, a typical example of which is the traveling salesman problem, in which there are many cities on the map, and the task is to visit all the cities once and return to the original position as shortest path as possible. So we have to minimize the tour length or the cost function. The cost function is the generic name in combinatorial optimization problem to be minimized. And another example is the lattice protein folding, in which amino acids are placed on sides or vertices of a lattice for simplicity, and you try various configurations of those positions to identify the lowest energy state. And since we are putting amino acids on the lattice, the directions between two amino acids are discrete. So they can be represented in terms of zeros and ones. So the problem is to identify the lowest energy state given the value of this sequence of bits. So this is a classical problem in the sense that nothing quantum mechanical aspects appear here. So a formal formulation of combinatorial optimization problem goes as follows. It's to minimize the cost function of discrete variables. Since discrete variables can be represented in terms of a series of bits, zeros and ones, that can be easily translated into plus or minus one, a set of those so-called Ising spins. And the Ising model of statistical physics has the energy function, or the Hamiltonian, or the cost function, typically of this form. Sigmas are Ising spins, plus or minus one, given at each site or at each variable. And in this typical example, the cost function is a quadratic function of sigmas with coefficient jij. But your problem of combinatorial optimization may not be represented in terms of this simple quadratic form. It may have a linear form or third order term. But the story that I'm going to tell you about today does not depend upon the details of the form of this Hamiltonian. So let me take this very simple form of quadratic Hamiltonian, or the cost function, or the energy, which should be minimized as a function of the Ising spins, or bits. So the lowest energy state of this cost function is called the ground state in physics. So I will use this term frequently. And often, those Ising spins, plus or minus one, are represented in terms of the arrows. Up arrow, an up arrow means plus one for sigma I, and down arrow for minus one. And a very well-known generic or metaheuristic method to solve such combinatorial optimization problems is simulated annealing. So this diagram shows the value of the cost function as a function of the state, or the configuration of spins, ups and downs. So if you give a configuration of spins, or the series of bits, like here, up, down, down, up, then the value of the cost function is given, uniquely given here. And in simulated annealing, you try to change the state by a small amount. For instance, the upper left spin has been flipped from up to down, and you calculate the value of the cost function for the new configuration. And since the goal is to find the ground state, or the lowest energy state, then if the new configuration has has a lower energy or lower value of the cost function, then you accept the new configuration as the updated candidate state. But even if you have a higher energy, then you accept that new state with the probability e to the minus delta divided by t, where delta e is the difference between the cost function, the new state minus the old state. And t is a parameter called the temperature. You accept this uphill motion, because a beta state may go beyond the hill. And this parameter, T, temperature, is kept very high initially. So the probability is equal to 1, because inverse T is close to 0. So initially, the system hops from state to state very frequently, looking for the best state in the whole space of the states. And you gradually decrease the temperature to a lower value, to lower values. And in the end, you set the temperature to 0. And if successful, the system will be in the ground state of the whole space, which is here. And this is a very well-known method proposed in the early 80s. And the paper by Scott Kirkpatrick and company has been cited almost 20,000 times. It's a big breakthrough in the field. So this is classical in the sense nothing quantum mechanical shows up here. And as a physicist, I was curious, what happens if we replace this classical thermal hopping process by quantum tunneling processes? So we called it quantum annealing instead of simulated annealing. It's also a metaheuristic in the sense that it can be applied to any problem if the problem has been formulated in terms of the Ising model, the Hamiltonian that I wrote before. So initially, similarly to the simulated annealing process, we let the system evolve, looking for the best state among all states uniformly. But the sense of uniformity is different because we accept a quantum mechanical linear combination of all states. So the probability is uniform in the quantum mechanical sense initially. So from this state with very large quantum fluctuations, we gradually control the strength of quantum fluctuations toward 0, following the Schrödinger equation, the natural time evolution of the system of the microscopic world. Then we hope that the quantum mechanical probability will gradually concentrate on lower energy states. And in the end, if successful, the probability will be sharply peaked at the ground state or the lower energy state. So this is the basic idea of quantum annealing. And it sounds fancy to physicists, at least. It's interesting. But does it really work? Quantum mechanical tunneling is effective or not? This is the first question we asked ourselves, and answer turned out to be yes, in the following sense that I will describe. And if it works, is there any reason to use quantum fluctuations instead of thermal classical fluctuations? In other words, is it better than simulated annealing or not? And surprisingly, we found the answer is yes, in some sense, which I will describe shortly. So let me show you some of the first pieces of evidence that support those conclusions. So we took a very small system, just 8 spins, 8 variables, plus and minus ones. And those spins have been connected by random interactions. This is the so-called the Sherrington-Kirkpatrick model of spin glasses. If the size is very large, to identify the ground state configuration or the lowest energy configuration of this problem is known to be very hard. But the system is small, so it's a test bed. And we control the strength of the quantum fluctuations, which is written as gamma of t here as a function of t in this form, 3 divided by the square root of t. So if t is small, that is initially the quantum fluctuations, the amplitude of quantum fluctuations is very large. And as time goes on, 3 divided by square root of t decreases. So in the end, it's very small. So we solved the Schrödinger equation directly for this small size system. It can be solved directly because the number of states is 2 to the 8th. It's 256, which is small. And this graph shows the probability P of t, which for the probability that the system is in the ground state at the given time t. The wave function as the solution of the Schrödinger equation is composed of a linear combination of all states with appropriate coefficients. And for this small system, we know the ground state from the outset. So we looked at the coefficient of the ground state. And the square root of this coefficient gives the quantum mechanical probability that the system is in the ground state at the given time t. So as you see, this probability increases monotonically as time goes on. And apparently, it approaches 1 in the end. So in this sense, at least for this system, quantum annealing works. And it works better than simulated annealing in the sense that the probability exceeds the corresponding probability of simulated annealing, which is plotted in the second curve here. And in simulated annealing, we control the temperature, capital T, as a function of time t in the same way as we control the strength of quantum fluctuations, 3 divided by square root of t. There are reasons to directly compare gamma and capital T. If you are curious, I can answer, but let me just go on. Just believe me, it is legitimate to accept the same functional form of those functions. So if you drive the system in this way, thermally, by solving the master equation, which represents the probability that the system is in the ground state or any other state by simulated annealing processes, we found this curve. So asymptotically, it seems that this curve for the classical process doesn't reach 1. In this sense, of course, it is not negligible. It's close to 0.6. So if you repeat this experiment twice, then with high probability, you expect that system will find the ground state. But in quantum annealing, you can expect it just by a single run. So in this sense, quantum annealing is better than simulated annealing, at least for this system of small size. And after this initial indication, a lot of groups in the world carried out similar numerical tests. And in almost all cases, they found comparable results. That is, quantum annealing finds the ground state with higher probabilities or closer states to the ground state with higher probabilities. An example of which appears here. And this is a big system, 1,002 cities in the traveling salesman problem. So those people from Trieste ran quantum annealing by sampling, that is quantum Monte Carlo simulations. And this graph shows the time dependence of the error, which is called the residual energy here. And they ran simulations classically and quantum mechanically for finite time, tau. So after a finite time, tau, you may not expect the system has reached the ground state. So there is an error, which is plotted as a vertical axis here. So h of tau is the actual value of the energy that they have reached after a finite time tau. And E true is the true ground state. And the difference is called the residual energy. So this should ideally be 0. So the smaller the value along this vertical axis is, the better the result is. So if you run the simulations longer, that is along this direction toward the right, the better the result you expect. And the data shows that tendency. But you see that the curve for simulated annealing has a shallower slope, although the functional forms are very similar. This form, that form. So qualitatively, those two methods, quantum and classical, may be similar, but quantitatively, in the sense of the slope, quantum annealing is better. This is their result. And there exist many other pieces of evidence that quantum annealing is better than simulated annealing in this sense. And of course, there are a limited number of exceptions in which simulated annealing shows better results than quantum annealing, which is one of which is written here. This is for the 3 satisfiability problem run by the same group from Trieste. So in this result, the slope of the simulated annealing data is steeper than quantum annealing. So quantum annealing does not always beat simulated annealing, but in most cases it does. So it's a bit puzzling, but it's interesting. So the next question is there any theoretical background to support those results from numerical experiments? And the answer is yes. It's the convergence theorem for simulated annealing first, which was proven by those people in the early 1980s. They proved the following statement. In simulated annealing, the variable temperature, capital T as a function of time t, lowercase t, should be controlled this way. Constant, problem-dependent constant c times the system size n divided by the log of time. Then, in the infinite time limit, in the end, you are guaranteed to reach the ground state, the minimum energy state, with probability 1. It takes an infinite amount of time, but it is guaranteed that you end up with the correct answer. And this is a very strong result, and at the same time, a weak result. It is strong in the sense that it applies to any problem, in the world, even the most difficult problem can be covered by this theorem. So this is a very strong generic result. And it is weak in the sense that it covers the worst problem in the world. So in practice, you don't have to control the temperature in this very slow manner. You can decrease the temperature more quickly, linearly, or even exponentially fast. And yet, you may reach the ground state with high probability. Anyway, this is the mathematically rigorous theorem, which is the backbone to run simulations by simulated annealing. So we asked ourselves if we can establish something similar to this result. And we could do it. The variable gamma as a function of t is the coefficient of the quantum mechanical term. You don't have to worry about the details of the expression, but gamma should be compared to t. So gamma as a function of t is to be decreased as a function of time, like this t to the minus constant, problem-dependent constant divided by the system size n, such that the system reaches the ground state with probability 1 in the infinite time limit. This is a theorem to be compared with the Giemann theorem for simulated annealing. So again, this is a very strong result and very weak result simultaneously, in the sense that it applies to any problem. It covers all the problems in the world, in the universe. And since it covers the worst problem in the world, it is a very slow decrease for a given specific problem, which may not be the worst problem in the universe. But these theorems apply. These theorems assure you that you get the result, correct result, in the infinite time limit. But you cannot wait forever. Your lifetime is limited. A student has to write a thesis within 3 years, typically. So you should stop somewhere. So what happens if you stop at some finite time? So suppose that you stop the process at time t, and the temperature for simulated annealing, capital T, is very small, is said to be very small. And in statistical mechanics, it is known that for very small temperature, the residual energy, which is the energy between the true ground state and the obtained state, is of the order of the temperature. So delta E, the measure of the error is delta E, which is comparable to capital T, which is said to be a small value delta. And as I said, the temperature is, in the worst case, controlled in this manner, constant times the system size divided by the log of T. And if you solve this problem, this equation for time t, then you get the final expression. T is equal to the exponential of constant times n divided by delta. So the time to reach a small value of error is exponentially large. This is very natural because you are talking about the worst problem in the world, and the computational complexity is exponential in the system size. So in this sense, there is no surprise. And what can be said about quantum annealing to be compared with this result? According to quantum mechanics, for a small value of gamma, the quantum term, the error from the true ground state caused by a small value of gamma starts from the second order perturbation, because the first order perturbation, which is linear in gamma, vanishes. So the error is proportional to the gamma square. which is said to be a small value delta. And gamma is controlled, as I said before, t to the minus c divided by n. So t to the minus 2 c prime over n is said to be a small value delta. And you solve this equation for t to obtain the final expression, which is t equal to e to the n log delta divided by 2 times c prime. So again, the computational complexity is exponential. So this is no surprise once again, because we are treating the worst problem in the world. So is there any advantage to use quantum annealing? Both are exponential. It's the difference in the coefficient. If delta is very small, then the coefficient in the classical case is very large. For instance, if delta is 10 to the minus 6th, then the inverse is 10 to the 6th. But log delta of 10 to the 6th is of the order of 10, which is much smaller. So in this sense, quantum annealing is better, theoretically. So this is a sort of backup for the numerical result that I showed you before. And there is an interesting aspect of this result. This is the convergence condition for quantum annealing. Gamma of t is equal to t to the minus constant divided by system size. But what is t here? It is the real time appearing in the Schrödinger equation, naturally. But at the same time, we could prove the same result for a quantum Monte Carlo implementation of quantum annealing, stochastic processes. You map the quantum problem into a classical problem by introducing many copies of the classical state. So those copies, the differences between those copies represent quantum fluctuations intuitively. And so in this mapped picture, everything is classical, because quantum fluctuations have been reduced to the difference between layers or the copies. And you run the usual classical Monte Carlo simulations by flipping spins one by one, classically. So the time appearing here is not the Schrödinger time, real time, but it's Monte Carlo steps. And yet, you find the same functional dependence of gamma for convergence conditions. I don't know why. I know the mathematical structure, but I don't know why intuitively. This is still a mystery for me. So this is a small detour. Anyway, let me give you a bit different aspect of quantum annealing, which is quantum adiabatic computation. The essential ideas are the same, but a formulation or the viewpoint is a bit different. So you start up with a state with very strong quantum fluctuations, which is a state with only the transverse field. So initially, the spins, originally spins point either up or down. But if you introduce quantum mechanical fluctuations, spins may point to the x direction, not z, but x direction. And since the field is very strong initially, all spins point to the x direction. This is a very trivial state. So you start from this very trivial state, and you let the system evolve according to the Schrödinger dynamics. And in quantum adiabatic computation, you enforce the system to stay within the instantaneous ground state during the course of time evolution. And in the end, if successful, you keep the system in the ground state as well in the end. And in the end, you only have the cost function, the classical cost function written here in terms of Ising spins, the ground state of which is a non-trivial state. So you start from this very trivial state and end up with this very non-trivial state. So this is the picture of quantum adiabatic computation. But in practice, the gap between the ground state, the lowest energy state, and the next lowest energy state, the first excited state, may be very small. The delta may be very small, in which case the time evolution may not follow faithfully the ground state, but the system may jump onto the excited state. So you should be very careful if there is a small gap in the course of the evolution, which is often the case. Let me give you a small detour. It's a frequently asked question. What is the difference between quantum annealing and quantum adiabatic computation? Well, the ideas are the same. We use quantum fluctuations to drive the system from the trivial state to the non-trivial final state. But as the name indicates, in adiabatic computation, you insist on keeping the state in the instantaneous ground state as faithfully as possible. But in quantum annealing, you may allow the system to hop to higher state with some probability. So you try the process many times. So graphically, according to my understanding, quantum annealing includes quantum adiabatic computation as a special case, but it's broader. So the processes realized in the D-wave machine are quantum annealing, I understand. So anyway, what is the computational complexity from the viewpoint of quantum adiabatic computation? It's related to the gap, according to the adiabatic theorem of quantum mechanics, according to which the time tau, the total time tau necessary for the system to stay faithfully in the instantaneous ground state is proportional to the inverse square of the minimum gap. And if the gap closes very rapidly, e to the minus constant times the system size, then the time necessary to reach the true ground state grows exponentially, which means that the problem is very hard. It's virtually impossible to solve it on the given computer. But if the gap closes relatively slowly by a polynomial power of the system size, then the gap closes. Then the time necessary to reach the ground state grows only polynomially, which means that the problem is easy. And in the gap closing point, often a phase transition happens. And for first order phase transitions in which physical quantities jump from this value to this value, this behavior is called the first order phase transition. Then it is often the case that the gap closes exponentially because these states are completely different. Physical quantities jump, so this state, this phase is completely different from that. So this difference should be diminished very quickly, which means that the gap closes very quickly. In contrast, in second order phase transitions, in which quantities change continuously, although the derivative may jump, then the gap closes. The gap is known to close polynomially. So the order of phase transition matters. And there is a typical example of a first order phase transition in which the problem is trivial. All spins, all arrows should point up. this is the correct solution. So the solution is trivial. You start from this trivial state, and you are asked to reach this trivial state. And yet, there is a first order phase transition. This is axis of gamma, and this is the axis of the gap. So for small sizes like this, the gap has a relatively mild minimum. But as the system size grows, the behavior of the gap becomes sharper and sharper. And for a very large size, it almost jumps from here to almost 0 and another value here. So the gap jumps in the large size limit. And it is 0 exactly at the transition point of first order. And the right panel shows the behavior of the gap as a function of the system size in the semi-log scale. Since it's linear, it shows an exponential decrease of the gap for various values of p, 3, 5, and so on and so forth. So this is an easy problem that cannot be solved by quantum annealing. So it was a challenge for us. Is there any way to circumvent this difficulty? And the answer is yes. We introduced, so here is another diagram that shows that difficulty. Here is the axis essentially of gamma, which is written vertically now. You start from this trivial state, and you want to end up with this trivial true solution, but there is a first order phase transition. But we found that if you introduce an extra term of quantum fluctuations, sigma x at different sites, I and j, then you have another coefficient for this new term. So the diagram extends to a two-dimensional space. And you have another degree of freedom. And we analyzed the phase diagram, the order of phase transitions in this two-dimensional space. Then we found that this first order phase transition disappears at intermediate point and is replaced by a line of second order phase transitions. So if you follow this path by using another quantum driver Hamiltonian, you can avoid the difficulty of first order phase transition and reach the ground state. So there are ways to avoid such difficulties. Is this method specific to this very special trivial problem? I don't know. We are seeking an answer to this question. But the indication is positive. And there is another piece of interesting result that we obtained recently, which I don't explain in detail, but just look at this picture. This is another different problem. But all those four pictures show the dependence of the gap as a function of the system size for various parameters appearing in the problem. So usually, if the gap closes exponentially fast, which means a difficult problem, then you expect the behavior of the gap this way, an exponential decrease. But in this very anomalous case, the gap changes very rapidly, as you see, or like this, or like this, or like that. If you follow the number of sites, so the system size, one by one, following the natural series of natural numbers. But if you choose the right sequence, for instance, if you follow the envelope of this set of data, then the gap closes polynomially, 1 over n. But if you follow the wrong sequence, the gap closes exponentially. So there is a room of choice of the sequence of the system size. So even this is an example of first order phase transition. So even if you encounter a difficulty, you may be able to choose the right sequence of the system size to get a good result in this anomalous case. I don't think this is a generic feature of first order phase transitions, but we should keep it in mind that there is such an anomalous case. So let me skip the details of the problem to save time. And if you are curious, I can answer the question. I can answer questions, but let me summarize my talk. Quantum annealing works. And it works better than simulated annealing in the sense that I described. And even if you encounter a difficulty of first order phase transitions, there may be ways to avoid those difficulties by choosing the right quantum fluctuations or by choosing the right sequence of the system size. Thank you very much for your attention.
So I was quite intrigued by the bound you gave of quantum Monte Carlo and quantum annealing, even though quantum Monte Carlo is classical. Can you say a bit more about that?
The same functional form appears. Yeah, yes? 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 You want me to explain it once again?
I understood what you said. So I understand the statement, but I find that quite intriguing that it's different from
amazing,
simulated
yes.
annealing, even though quantum Monte Carlo is also a classical algorithm.
Yes.
So maybe you could give some idea of...
No. Honestly, no.
Okay. So you're as intrigued as me, I guess.
Yes, it's, well, as Feynman said, I never understand quantum mechanics. I know how to manipulate equations, but I fail to explain intuitively always. In that sense, the performance, the fact that quantum annealing works itself is a mystery for me. And even quantitatively, classical and quantum implementations have the same functional form. It's a mystery. I'm sorry, I don't know. More precisely saying, the statement is as follows. In the Schrödinger dynamics, the variable gamma should be controlled precisely this way. But in the quantum Monte Carlo implementation, the asymptotic form of gamma looks like this. For small value of t, it has a bit different functional form. But for large t, it reduces to this expression. This is a precise statement.
I didn't get any sense of what your proof technique is for showing that the quantum annealing converges, because, I mean, you didn't hint at your proof technique. And I would like to know also whether your proof technique requires that your Hamiltonian be stochastic, which means that all the off-diagonal terms have the same sign, so you can do quantum Monte Carlo simulation.
The technique for the Schrödinger dynamics is to use the adiabatic theorem itself.
For quantum annealing, that's
Yes.
what you use, is the adiabatic theorem, okay?
Yes, and for the quantum Monte Carlo, do you hear me?
Yes.
For the quantum Monte Carlo implementation of quantum annealing, we map the problem to the classical. We map the quantum annealing to the classical representation by introducing Trotter slices, and we apply the method of Giemann and Giemann to that classical problem.
But when you do the quantum annealing, so you actually estimate the gap. than for,
yes.
but you seem to be,
Yes.
but you said it works in all
Yes,
cases. So that must mean you have a lower bound on the gap in all cases. Is that right?
Yes.
Do you have a lower bound on the gap?
Yes. It's yes.
And how do you get that lower bound?
We use the Hopf theorem, which says that any a type of you are given a type of matrix, and the Hopf theorem gives the gap between the largest, in some sense, eigenvalue and the next largest eigenvalue. There is a mathematical theorem called the Hopf theorem that is very useful for this purpose.
Okay, thank you.
You're welcome.